All right, so we're back into this. So n is 1.5, and we're going to subtract 1 from that. And then 1 over R1. And if you look at how R1 is curving towards the right side, that's concave towards the object would be how I would take that. Concave towards the object is going to go in as a negative minus. And if I'm sticking with this side over here on the right, then R2 is convex towards the object. So I think this goes in here as 50. So then we're going to Desmos this business. Let's figure out. Okay. There we go. All right, so boop boop. So when I put 1.5 minus 1 times that stuff into Desmos, so I get negative 0.03083s. And then the thing I wasn't thinking of straight away is that's equal to 1 over the focal length. So if I take the inverse of that, let's see what that does. That's going to give me negative 32.4 as the focal length. I'm not 100% on trusting that. Why am I getting negative there? So I don't know. In this problem, if it tells us which side the object is on, that's impacting whether I get a negative answer or a positive answer. So when I run it like this, if I'm treating it like my object is on the right side, then I would say R1 is concave towards the object and R2 is convex towards the object. So that's why I have the signs as I do in here. I have the 24 as negative and the 50 as positive. If I do that, I get negative 32, which makes me think that I'm finding something on the other side of the lens. But if I make the 24 positive and I make the 50 negative, then I get positive 32. And that's the keyed answer here. So I don't know if anybody pulled anything out from the reading that made it clear. Yeah, Augustine, what do you think?
I saw the equation and that was all fine. It's just the problem I was having was that I wasn't focusing on basically the object being on one side, so you have a positive and negative focus. So a convex and concave side. I was focusing on it being both convex.
Got you. Okay. Yeah.
And so it gave me 100 as an answer, and I was confused.
Yeah, I'm not 100% myself on. This threw me off because when I was looking at the example, that I think there's an example problem in the book where it's like double. What do I want to say? The lens shape is like this. And so you had, if this was considered R1, and then actually higher maybe, would be R2. And they were both concave to the object on the side, and so that they both go in as positive. Is that right? No.
Yeah.
Concave towards the object, they both be considered negative. So, yeah, this is the one that I have a lot of familiarity with. Normally, when I'm done lens stuff, I've just dealt with the lens equations, so I myself am still kind of done. But I think that's the thing to play around with. Consider your object to be on one side, and then the contrarity of convexity on the determines positive and negative. So I don't know if that's helpful. Other questions related to the lens maker's equation? The thing I'm curious about too is like this 1.5 minus 1 to determine the focal length. I mean, it has it written as n minus 1. Is that because 1 represents the end of a vacuum? Do we put in a different number if we have this lens in water?
Yeah.
Would we write 1.5 minus 1.2?
Yeah, because
It's going to change the focal length.
Yeah, when it shows the derivative, it like deriving the formula from taking the different values.
Yeah.
It does show that process, and then it basically just says that it gives the generalization almost.
Okay, that's surrounded by error. Okay. Aight. Cool. Other questions related to the mastering? If you got questions on that, I think this week we're able to move around during EFT. That's always a good time. To pop up. What?
I actually had a chance to do.
Are you in here for EFT?
No, I had a chance to do something. I really.
Oh, okay. Okay. Aight.
Is it my answer? But I have to get some time. I haven't figured out the wrong.
Well, then what I would have you do is avail yourself of a ruler, for sure. And, oh gosh, let me come over here quick. Go back to scores view, my classes. Convex and concave mirrors. Oh, there we go. I'm just popping through the canvas, or sorry, the pivot from the weekend. All right, and that's kind of bonk. All right, why don't we take 7 minutes right now and catch up with your neighbor on the Curve Mirror Lab? The big thing that I'm interested in is like with number 4, finding the question 4 in section. I don't know, they don't really have section numbers. Question 4 in the first section where you're relating the radius of curvature to the focal point. Looks like a couple people have that, but that's just a couple people. So take a moment with your neighbor, go back through your canvas. God, why do I keep calling it canvas? Pivot, and we'll get where we need to get to. All right, so these are kind of the two that I'm keying in on the pivot as far as knowing that we're ready to move on with this curved mirror stuff. Question 4 and question 6. So could you please work with your buddies right now on getting those answered?
besides just doubling,
You do it in here, like,
is there,
it's the same here.
well, is there an actual, so we can algebraic equations instead of being calculus, or is
That I couldn't tell you.
because otherwise it's the inverse of the curvature, which, you know, is, which is, the curvature would be defined either by linear algebra, which you turn into the inverse of the matrix, or calculus,
I wonder if it was I'm just, all I'm wanting out of it is just the relationship. You know what? Yeah. Yeah, we're dealing with bouncing here now. Cool with finding the radius of curvature. Technically, yeah. The technical application.
What were we, like, I was gonna try to do, like, use like the thing, cause like the radius is right here, right?
Is it?
Yeah.
Just grab some lines and throw them on there and see. Yeah, the concave ones were more straightforward. It's convex one.
So I just did R with two. I was.
You got it for the concave, right?
I guess I only tried to convex, I saw, I could, yeah.
Yeah. These are fairly straightforward. Yeah.
So what do? You just draw them perpendicular to the.
Yeah. Just make a bunch of normal lines, see where they meet. And they should meet at double the radius of curvature.
Can you, return mine?
Yep.
Yeah.
Ooh.
We're doing it on the other. Yeah.
Teacher.
names are always.
All right, refresh it. It should work now.
Alright, thanks.
All right.
Creating what?
Gav, do you want to fire this up, buddy?
So you've drawn this. Like, you've drawn all the radius.
You get that out of my face. Get that out of here. I don't know what doing this stuff. What's the? What is this thing?
That's not right.
How do I spell? How do I spell Speaking of facts.
What'd you get? I didn't do. Which we can.
That took me a second to figure out.
Yeah. Hang on. Hang on.
If that was
Just a
So again, my primary interest in the analysis of this lab, making sure you're able to see a relationship between radius of curvature and the focal length. And then just from what you're seeing in the videos as you're collecting the data, can you come up with at least one rule for the ray diagram? Oh, shit.
Yeah, but I was a New York Pepper one this year. It's amazing, right?
I messed up like 5 times. Because I kept like pushing the.
This is the one time I say colors.
That's why I don't go like this. I go like this.
That would be a good idea, but unfortunately, I'm absolutely blind. I'm gonna keep doing this.
I just destroyed this.
I can spell radius of. I kept spelling radius. Radius.
Yeah, that first one. Wait. Actually, it looks like.
Yipes.
I see that. I see this big. Come on. I don't know what happened. I'm not like terribly allergic, but I think I'm mildly allergic. Unfortunately, I have
What?
absolute rat. Absolute rat.
Sorry, what? What was number three's,
Yeah, well, yeah, you can just do that. You can just pretend to be very guy and take the selfies. No, you just take your phone out and aim it at someone. But it's like, it's sorry, dude, I'm taking this on. Yeah, and so, yeah, when you put, yeah, and also when you put the phone catches the flash on the back bicep. Unfortunate.
Yeah, because you are not recognizable. No, you're.
Guys.
Yeah, because you're not recognizable. Yes, because someone on the yearbook table is a yearbook yearbook, so that's you. I run into this problem all the time.
I don't think I did.
I've been.
I was in sixth.
Not even my freshman, not even my like personal teacher. I just don't show up.
Oh, 2 years, last year it was in.
You leave.
Oh, yeah.
Vision, you
You're wondering why my picture isn't showing up on their nominations.
All girls professional.
Hey, look. Funky happened here. Funky, whoa. Whoa.
Whoa there, Shoddy. Shoddy vodka.
Jesus,
Yeah.
Get out of my head.
Say one thing.
All raised.
How did we get way different?
You always encourage
All right. So here's what I have for trial 3. I get the focal point. There was a little tool you could add in to like mark a location. So that's what I have there. And this doesn't hold for the edges of this mirror as well as it does for kind of the middle couple centimeters that it focuses parallel, paraxial, if you will, rays through a point at about 12 centimeters. And then I tried to estimate some normal lines to the surface as best I could. / I already knew in my mind where it needed to cross at. So I've got the radius of curvature for this mirror is about 24 centimeters. This mirror is concave towards the object side. And when we're talking about mirrors concave towards the object side, would mean that the focal length would be positive. And I think we can kind of see where I would hope you would go with number 6 based on what you can observe in the videos. What rule might guide how you draw this diagram for a concave mirror? So let's see what people have there. All right. So here's one example of what I see as an answer to number 6. What suggestions, if any, would you make for revising this statement? So, a rule to guide ray diagrams for curved mirrors. They say all reflected rays go through the focal point, which is 1/2 the radius of curvature. Concave makes the rays converge and can be upside down or right side up. Convex mirrors make the rays diverge. Image is right side up. So, any revisions to any of that statement that you would make? Augustine?
Maybe just make it like because in the video that the reflection first photon breaks down close to the edge.
Okay.
So if that can happen.
Okay. Why can't I spell necessarily? Necessarily? That wants 2 L's? I don't know. I guess this is the bit that I'm keying in on. All reflected rays go through the focal point. They do in this video because what's true of all the inbound rays? Parallel rays, yeah. So I would just make that revision. All parallel rays. So I would say all parallel rays are reflected through the focal point. Aye. So here's another friend, and I would have similar beef with this. All rays? You're talking about all parallel rays. Or paraxial is their fancy pants term for it.
I'm so sure I have a good portion.
The ones that are parallel to the axis
Sure.
are going to be focused towards that focal point.
Whatever you say.
It's what the lab is doing, yeah? Because that's a downside or a limitation of the data you're getting here. You're only able to measure rays that are coming in parallel. We got another buddy saying this. So all parallel rays converge at a focal point. Focal point for concave mirrors is in front, for convex is behind. So mathematically then, this is a little different from lenses. A concave mirror, that's a positive focal length. A convex mirror, that is a negative focal length. So for our diagrams here, this will be better for you if you have a mirror. But if I send a ray parallel to the axis, it's going to reflect through the focal point there. And this is me doing a scan, so it's not great, but if you imagine, and this is the other thing I keep forgetting to do, we want to draw a line just like we did with lenses. Draw a line and have all the reflection occur at that line. So I'm kind of going into the mirror a little bit there. If you consider the surface of the mirror right here at the axis of symmetry, it's pretty much perpendicular to the axis of symmetry right there in the center. So a second ray would be one that is directed towards the middle of the mirror, and it's going to come off at the same angle. I wonder if I can copy this. And then can I reflect that? Flip vertical. That do what I wanted? Aye. There we go. Okay. So concave mirrors. Ray parallel to axis will reflect through the focal point. And then we would say a ray striking the center of the mirror will reflect at same angle to the normal. It's just following the law of reflection there. Theta I, theta R. And then the third rule, if you will, if I take this focal length and place it behind the mirror, I don't know how I'm going to approximate this, but if I tried to aim at it, if I try to aim a ray at it, that's going to bounce off parallel to the, that's really quality drawing there, Mr. Harding. So that would be rule 3. Ray aimed at focal point on far side of the mirror will reflect parallel to the axis of symmetry. And so that allows us to find the image location right here where these rays meet. They really do meet there. So this image is real and upright, although you can see it's somewhat reduced in size. So that's why when you stand over the concave mirror and you point your finger towards the center, I don't know what the radius of curvature for that mirror is, but you're less than a focal length away from the mirror. And that's why it tricks your eyes into thinking that you're actually seeing a finger coming out of that bowl, because the rays are really diverging from a point out in front of the mirror's surface. Visually, that's why it appears to really be there. So we can see that with those 3 rays. And I have this thing in here backwards. We want to try to apply those same rules to the other concave mirror diagrams. One where we're significantly farther away from the focal length, and one where we're a little bit farther away from the focal length. But we only got 2 minutes left. So we'll finish up with this business tomorrow. be mindful that long term, we're heading towards a test on Friday. So if you're not current on the readings from this chapter, chapter 34, this would be a good time to be catching up on that. And if you have questions on any of the mastering, make sure you're dropping me an email and I'll do my best to fumble through an explanation or some assistance. Oof. AP basics canvas. Buggy.
Palm side. Palm side.
Buggy challenge.
Palm side.
Oh, we do.
No, no.
Hasta luego.
You just imagine.
Getting smaller, she collapsed it up.
So it'd be like, this is 60 60
Hasta luego, my friend. Ah. PM. Oof. Shit. That's what I need.
You're supposed to have one, right? You what?
That's not what I need. That's not what I need. That's not what I need.
That's how it would be. Watching something. No,
That's not what I need. Damn it, man.
I understand it really well.
Physics canvas.
Then again, I was there Friday, so. The problem is, he has science homework that he doesn't talk about, so then I'm not.
Oh yeah, there we go. See you, buddy. Key 80. 80. 3. Start print. Oh gosh darn it. Let's see. What's up, Abdul? Yeah, please do.
What's going on, Alistair? You know, I'm looking for the best leg. Uneventful. Oh, come on. So you driving to school now? Yeah. Hell yeah.
I've been driving to school, but I haven't had to do it yet.
Oh, okay, I got you.
Why you? I'm 16, please.
Just do my day thing. Come on. I remember.
There we go.
On my 14th birthday, I was at the DMV getting my permit. On my 16th birthday, I was at the DMV getting my license. As soon as I was done with driver's ed, I was at the DMV getting my state permit. I was still ready.
I didn't have my, I didn't have
Blue.
So I would put it down.
like I passed the permit test when I was 14, but I didn't have.
All right, here's a week at a glance. Today, if you didn't finish up that motion graphing activity where we're just doing the odds, you can do that. Hopefully, it won't take too terribly long. Should be through most of it. And then I have something for you to work on with your group mates called a practice to model the problem. I'll talk a little bit more about that in a second. Tomorrow, we're going to introduce the challenge lab. So, give you the lay of the land. We're heading towards the end of the unit. You can see on Friday, I've got it listed as having a test on the constant velocity particle model. Thursday, there are no classes. This challenge lab, we'll introduce it tomorrow. And every unit of study this year, whatever, 8 or 9 units, you'll have a challenge lab at the back end. And to me, that's kind of the pretext. Like, if you understand how this model works and how to use all the tools, then it should go pretty well for you in the challenge lab. If the challenge lab doesn't go well, you got a couple days before the test to maybe fill in some of those gaps. So that's where we're at with this. There's not a whole lot to constant velocity motion. We got the slope on the position versus time graph. We got the area between the velocity versus time graph and the x-axis. And calculate those things. You're in pretty good shape here. All right. Let me look at this practice the model problem so I can talk to you about what that represents. Let's go. Class notebook. Oh man, physics 2. C mechanics. Today is 9-13. This is period 3. Practice the model. I'm still recording. I should probably shut that off. That would be smart.